I hope you had a great day yesterday. I had a lot of fun. It was great presentations and a great participation in the poster sessions yesterday. We're going to start our day today, and to get us started, to kick off the day, we have Feng Hao, who is an associate professor at the department or at the School of Electrical Engineering and Computer Science here at WSU. He is also an expert in cryptography. And the topic we have for today that he will be talking about will be on post-quantum crypto. And he is joining us virtually because he's traveling. He is actually in China now. I don't know what time it is in China where you are, Feng Hao, but thank you very much for taking the time to join us today. And I don't want to take too much into your time. Go ahead and get started.
Okay, so thank you, Asifa, for the kind introduction. So today I'm going to talk about post-quantum cryptography, which is a very interesting topic of my research. Okay, so we know internet technology is very important. It is building a connected world, so it enables a lot of applications such as online mobile banking, email, social media, and online conferences, so that even though we are far away, we can still connect with each other. So security of cyberspace is always very important. So privacy and authentication are important because there can be a lot of sensitive data in the cyberspace. For example, the user might download some private data from the cloud, and then if the adversary can learn that private data, and things could be very dangerous. Serious consequences can be there if things go wrong. For example, if adversary can say impersonate you and log into your bank account and transfer money from there, and this could be very bad. So an important technology to protect our cyberspace is public key cryptography. It is the foundation of HTTPS, and it secures email, secure payment, social media logins, and etc. So currently, we know there are two versions of HTTP. So one is HTTPS, which is the secure version, and has been used more often than the original non-secure HTTP. So the foundation of public key cryptography is mathematics. So we need math problems that are not solvable by even supercomputers. So there are only a few candidates, and fortunately, we do have such few candidates, such as factoring. So basically, the thing is you have a big number n, and the goal is to find the secret key p and q, which such that n is equal to p and p times q. And this is the RSA crypto system, the foundation. And there is another one called discrete log, which is the foundation of Diffie-Hellman key exchange. So due to the great impacts of those two types of crypto systems, so 2 Turing awards were given to the authors of those two crypto systems. So, but the foundation is challenged. So back to 1994, Peter Shor, an MIT professor who showed the first polynomial time quantum algorithm to solve factoring and discrete log. So this means theoretically quantum is more powerful than classical computer. So if the adversary could build a quantum computer at scale, it can break the RSA and Diffie-Hellman based crypto systems. So people were not so worried about that quantum algorithm because the technology was not there. So back to 2001, so the most say powerful quantum computer was in the lab, and it could factor 15 equals 3 times 5. And this is obviously too easy, not really meaningful. So it's not practical yet. But the technology advances, so towards building larger and larger quantum computers. So there are here is a very rough high-level time frame. So a number of qubits, you can think of this as a measure of how the scale of a quantum computer. So 1998, it was 2 qubit, and going to 2027, the number has significantly increased to 49, and 2019, it was increased to 53, and that was built by Google. And at that moment, the first time experimentally quantum supremacy was demonstrated. So this means for some specific task, we can experimentally show that quantum computers can do faster than classical computing. So before, we know factoring, yes, polynomial time quantum algorithms, but we cannot do experiments because we don't have at scale quantum computers. So since 2019, we do have some very specific tasks where quantum is more powerful. Whether this task is useful or not, this is a separate question, but definitely quantum computing is growing. So up to now, we might have more than 1,000 qubits, and hopefully researchers think maybe by 2030, we might have 1 million qubits. So one important thing is it's not, say, if it's not difficult to generate more and more qubits, but it's whether we can coherently control all of them simultaneously. So, but at this moment, we are facing a new reality. So quantum computing might, a scalable quantum computer might be there at some point. So to face this new reality, NIST in 2016 had this post-quantum cryptography standardization call. So industry has also participated in evaluate performance of those several post-quantum candidates, such as Google, Cloudflare, and several. So currently, a quick summary is traditional public key cryptography is facing a crisis because it can be obsolete eventually at some point. So we need new security infrastructure. So now this is a critical time to develop new sciences between cryptography and quantum computing. So we need new foundation for post-quantum crypto, and hopefully from that new foundation, we can build even more advanced crypto capabilities. So my research is two-part. So the first part is the basic mission. We would like to rebuild basic crypto tools against quantum computing. So this aligns with the post-quantum cryptography, the NIST current efforts, and maybe also future security of internet applications. So building this as a foundation, we would like to enable a much larger vision, which is to enable efficient, richer crypto capabilities. This includes computing encrypted data. This is known as fully homomorphic encryption, and applications to private machine learning and data analytics and numerous advanced crypto designs. So today I'm going to talk about, say basically, here is our roadmap. I will talking about some background and recent progress and several challenges and visions. Okay, so let's start with some background. So cryptography in general, so we need to answer two questions. So what is security and how to achieve security? So at a high level, we want no attacker can break the system. So what does that mean? So, and next, how to achieve security. So because we know there can be or could be infinitely many possible attacks. So how do we say secure something against the infinitely many possible attacks? So this comes to the modern cryptography, which developed very powerful paradigm. So the idea is we define a very clear security goal. For example, one is very classic security goal is called secure channel. So consider there are two parties and they want to establish a secure channel where they can communicate privately. So this means they can send private messages even in the presence of adversary. So adversary cannot learn anything about the message being sent. So how do we define it? Okay, so we need to formulate a notion that captures secure channel. So traditionally, people thought, hey, so by security we mean the adversary cannot recover the whole plaintext. But is this a good definition? So this is very tricky. So consider this example. So suppose the sender, which in this case is Princess Leia, and she sends or she tries to send this "Help me, Obi-Wan Kenobi, you are my only hope." So if the adversary, even if the adversary in this case consider adversary cannot figure out the whole message, but if the adversary can figure out some partial message, in this case is Obi-Wan Kenobi, and this is considered insecure. Okay, so what we really need is adversary cannot learn anything. And this is formulated and proposed by Goldwasser Mikali back to 1982. And this is the foundation of how we think about cryptography. So how do we capture this? So we consider a mental experiment where there is an imaginary dummy message. In my example, this is Empire is the best. So by sending a real message or an imaginary message, adversary cannot tell, hey, by seeing something being transmitted, he cannot figure out whether the orange message or the blue message was sent. Okay, so this is not just a very theoretical, highly theoretical thing. This type of security has been explicitly requested in the NIST post-quantum cryptography call. It is in the call for standardization, the white paper explicitly. So this means the theory behind it is very important. Okay, so the next question is, okay, now we have a very clear security goal and security definition. How do we realize the security goal? So because in reality, there is no physical secure channel. So the thing is we can construct a mental ROI using mathematics. So this is called encryption. So consider this ciphertext, and this ciphertext carries some message. Okay, so you encrypt this ciphertext, and the other party, which has the corresponding secret key, can recover the message. An adversary who doesn't have the secret key cannot distinguish whether this droid carries the orange message or the blue message. So this is how we can realize the security goal. So the next question we want to address is how do we prove security against infinitely many attacks? So in order to do this, a very powerful framework called reduction framework was proposed. So the reduction framework has three parts. So the first part is math problem, and the second design, and then reduction. A reduction is also known as proof of security. So pictorially, it looks like this. We design a crypto system, and based on some hard mathematical problem, and this mathematical problem might not be explicitly related to crypto system, but Yeah, it is just a very clean mathematical problem. So by building this reduction, we can show if we need to show if an adversary can break the crypto system, then there exists a reduction that can solve the math problem. So logically equivalently, this means if the mathematical problem is not solvable, then no adversary can break the crypto system. So the crypto system is secure. So now we reduce analyzing the security of crypto system to harness of the solving the mathematical problem. So now, where do we find these mathematical problems? And fortunately, we have some candidates. For example, some RSA discrete log. And from those problems, we can show secure crypto systems. So in the quantum era, so under this quantum computing, the RSA and discrete log, the underlying mathematical problems are no longer secure, or no longer hard because they can be solved by the quantum computing. So now, what we need, because this framework, so even though the mathematical problems can be solved by quantum computing, the whole framework is still valuable. So the hope is we find new hard problems against, say, quantum computing, and can we design new crypto systems and proof of security? So now the crypto lesson we have learned so far is theoretical foundation that even in the pre-quantum era matters. So because this is a modular design, and we hope we can do this plug and play. So hopefully we have some PKE public key encryption abstraction. And from this public key encryption abstraction, we can build several secure applications. And before we know how to realize these public key abstractions from RSA and discrete log, now we just need new math problems. And hopefully we can just plug and play. So we just replace those previous RS and DL based crypto systems by the new mathematical problems. So this shows our 327 is very important because we are like going over all these frameworks and the modular design. Okay, so hopefully, if for those who haven't taken 327, I look forward to seeing you in the next semester. Okay, so now let's talk about some recent progress. So NIST post-quantum core, this aims to standardize future post-quantum cryptography, and this was an effort starting 2016. So NIST claims in order to migrate a system from old system to a new system, it can take more than 20 years for migration. So this, you might think, hey, migration, how hard can that be? But in reality, so we need to, it's not just like you click a software update and or upgrade and then you are done. Because you also need to think about different timing of compatibility between new system and old systems. And the weakest link might happen from the old system. Okay. And another thing is it is kind of not that easy. Not every math problem is like a plausible against quantum computing. And how do we set specific parameters? How do we implement the crypto systems? And how do we deploy those everything, every little detail can be challenging in reality. So Nice says, hey, we should do it sooner than later. And it was very great that NIST had this call 10 years ago. So now we need new math hard problems and crypto designs. And there were a lot of different directions proposed, like code-based crypto, lattice-based, hash-based isogeny, multivariate-based, so on and so forth. So say so for NIST progress, so for the third round, NIST has already identified several candidates for public key encryption and signatures selected for standardization. So several of them are lattice-based and one is hash-based. And in the fourth round, there is another one, HQC, which is a code-based crypto system selected for standardization in 2025, last year. So kind of at this point, we have different candidates and selected for standardization. And there are still a lot of research going on. So NIST, the logic of NIST is we don't want to put all the eggs into one basket. So we want to study different levels, different types of, crypto systems. So, but during the selection process, cryptographers, sometimes we just cannot sleep because many candidates were broken. So one was like a very famous called Rainbow, which is a multivariate signature. So it was kind of a very promising candidate towards the third round, but it was broken. Yeah, published at Crypto 2022. And there is another one, Psych, which is an isogeny-based crypto system. It almost like advanced to the fourth round, right? But before the selection, say at EuroCrypt 2023, it was just completely broken, and there is no easy fix for the Psych. So still plausible. So lattice hash code base and still some other types of isogeny-based isogeny hard problems are still plausible, but just not Psych. Okay, so that is very, very interesting development. And every candidate here, there had been a lot of efforts, even if broken, right? A lot of research, a lot of researchers' efforts behind each scheme. Okay, so now let's go a little bit further into the lattice-based crypto, because this is also my research, and there are many other interesting things going on. So then, say lattice-based cryptography is a new hope towards post-quantum cryptography because there are a lot of advantages, such as efficient operations, and this is a very classic problem, resistance to quantum attacks, and right. And this is also a foundation of a lot of advanced crypto systems. Okay, so we will talk about those interesting applications and advanced crypto systems. So one thing, the foundation of lattice-based cryptography is called a very important problem, learning with errors. And this is, has been attract a lot of attention in both theory and practice. So we have new post-quantum candidates in theory, public key encryption, signature key exchanges, and three variants, as I just mentioned before, are selected for standardization by NIST. So in addition to the basic, crypto, lattice-based crypto also allow computation on encrypted data, which is known as fully homomorphic encryption. So it is can be used widely in secure outsourcing computation. And according to DARPA, this FHE, fully homomorphic encryption, is holy grail to keep data secure while in use. So consider this example. So suppose the user has some data and she wants to outsource that to the cloud. Instead of sending it in the clear, she can encrypt it and send it to the cloud and request some computation later, and the cloud, without decrypting the data, can still perform some computation on the data. So this is called homomorphic computation. And now the user can just decrypt and learn F of data. And this fully homomorphic encryption supports arbitrary computation of F. Okay, so application to multi-party computation. So this is a very classical solution to the Yaw's millionaire problem. So the problem says, suppose two parties who hold private input X and Y, they want to determine which one is larger without revealing the numbers. So this it can be some kind of application to e-finance, for example. You want to compare numbers that are confidential, whether your bank saving is greater to some kind of threshold. So to achieve this, say the one party just encrypt the input and the other party just compute F, which is a comparison function, and outputs 1 if X is greater to Y, otherwise 0. So, and this, say Yaw's millionaire's problem was kind of a little bit back to 1980s, is a little bit old-fashioned, but so in today there are more modern, very cool new applications. So one application which we want to say is this machine learning as a service. For example, your input X is some kind of picture and your Y is some machine learning model, and say they want to, the user wants to say ask, hey, the cloud whether you can do some prediction on the data. Okay, so now the user wants to outsource the analysis, but without revealing the input, and the cloud also doesn't want to reveal the model Y. So how can they do this? So fully homomorphic encryption provides an elegant solution to this picture. So this is really a triumph for crypto theory. So theorem one, under LWE, there exists a post-quantum public key encryption. And theorem two, under LWE, there exists post-quantum fully homomorphic encryption for arbitrary function. And theorems 3, 4, 5, under LWE, there exists a wide array of advanced post-quantum crypto systems. So in place of LWE, one Gödel Prize was given to the inventor, Oded Regev. So the citation says, it serves as the foundation of countless subsequent work. It is a revolution in cryptography in both theory and practice, and it is a simple yet amazingly versatile foundation for nearly every kind of cryptographic object. So in a nutshell, what is LWE? So at this moment, this is a kind of a problem inspired by machine learning. So the title has this learning, but also with errors. Okay, so consider this setting. There is a secret information, secret vector S in this box, and the user has some click, okay, remote. And by clicking the button, she receives a random vector A1, and a B1 equals A1S plus error. And she can do this multiple times, and the goal is to find S. So if there is no error in the equation, then any adversary can easily solve S by Gaussian elimination. But in the presence of errors, and even very powerful quantum adversary cannot learn the secret, or at this moment, no one know that we don't know any quantum algorithm that can solve the secret. So, however, the LWE-based constructions are not very efficient because of large key, large ciphertext, slowing computation. So how inefficient? So we kind of do a very rough estimate. So the public key cryptography, the length is roughly a size 1 MB. And if you want to do the noise sampling in the encryption process, it's very, very slow. So if we compare this with our quantum RSA, the public key length is just 3,000 or 4,000 bits instead of 1 MB. Okay, so no NIST candidate really uses this exact sampling procedure and the LWE problem, let's say, as is. So the research goal is, hey, can we improve efficiency? Okay, so to improve efficiency, there are several different directions. So one is using more algebraic structure. So for example, we can use polynomial rings. And to improve computation efficiency, there is another technique called rounding. So instead of adding noise or simple random noise, we just use deterministic rounding and to say to make this much faster. So the fundamental question is, are these variants of LWE hard? Because with additional structures, this can affect security. And if you do rounding instead of adding error, this is a variant, but who knows, this variant is hard. So crypto is subtle and sensitive because insecurity comes from nuances. So some of my research, I kind of show the ring plus rounding variant is as hard as ring LWE. And prior work showed ring LWE is as hard as some ideal lattice problems, which we think or we are not aware of any quantum algorithms that can solve the ideal lattice problems. So by putting these together, we can show that ring plus rounding is as hard as some ideal lattice problem. So, okay, so this is some of my research. And more of my research is we want to answer, is FHE fully homomorphic encryption solution based solution practical? Because I just drew the picture of private machine learning as service. Theoretically, this is possible, but can we really deploy this in a real world? Is this the latency practically acceptable? So in order to do this, we kind of need to squeeze research from all directions. So particularly, we need more efficient crypto and FHE methods. Okay, so the second direction is we also need to design fully homomorphic friendly machine learning model. Okay, so it's not just from crypto, we also squeeze from machine learning side. And also we consider hardware acceleration such as say GPU, FPGA, or ASIC. So these are different types of hardware that can significantly accelerate, say, the computation. So by squeezing all these directions together, we hope that we can make, say, FHE-based solution, say maybe 1 or 2 orders of magnitudes slower than the plain text computation. Okay, so finally, I would like to talk about some challenges and visions. And this is a little bit, so if we zoom out the research zoom out post-quantum cryptography, say machine learning as a service or private machine learning as service, we kind of want to answer a little bit more philosophical questions that, but anyway, so if we have a time machine and we go back to 1990s. So 1990s, we know like Internet of Things have started, okay? And at that moment, uh, cryptography is significantly important because we want to build secure communication. We want to build, say, e-commerce, online banking, and a lot of things. So public key cryptography standardization played an important role of that time. So we do benefit a lot from the technology. It's not just military. It's not just the several a small group of people. It's kind of everyone. Say today, it, for everyone sitting here, implicitly or explicitly, we are using cryptography, and we benefit a lot from the technology development. So, 2010, there have been a lot of great, say, crypto breakthroughs. For example, foundation of post-quantum cryptography, lattice-based cryptography, theoretical breakthrough of fully homomorphic encryption, and also there is another thing called blockchain, and which is also developed, which was also proposed and soon becomes very, very, say, a buzzword. Okay, so from 2020, it's kind of a time for us from theory to practice. So we have developed beautiful, say, theory of fully homomorphic encryption, and now we can build privacy-preserving machine learning and much more practical fully homomorphic encryption and also multi-party computation, those type of things. So, but at this moment, we want to ask, hey, is it at this moment, whose privacy is really protected? Is this really relevant to you? For example, for blockchain, uh, so is this kind of a new technology that benefits you, or it just benefits for those capitals who just can say may make a fortune out of it? So this is something I'm not against blockchain, but I'm just saying this is something we should think about. So for privacy preserving technology, whose privacy is protected? Is that your privacy? So suppose you outsource your data to Amazon, and Amazon is using some privacy preserving technology to sell to match your data with some advertisements and then earn a lot of money out of it, and then you earn nothing. Is this kind of justified? So this is something we should think about. And now, so 2025, 26, AI is everywhere. AI assisted cryptography and secure design, and AI defense, AI assisted, say, offense. This is kind of a new trend that researchers we need to think about, and even in the post-quantum era. So, um, but on the other hand, there are other new issues. Does AI make the world safer? You can think, yes, it improves the way it can help us, um, say, design crypto, but it can also help the adversary exploit, say, even more possible, say, vulnerabilities. It might not be the mathematical vulnerabilities. It might be the system design, implementation level, and deployment level. So really, does AI make the world safer? This is hard to say. And are you happier? or more stressful under this new AI reality. So this is something, yeah, we also need to think about. So finally, I would like to conclude my talk here. So um, we, for researchers and cryptographers, how can we make the world better? Now we have more crypto techniques, but we also have more powerful adversaries. For example, quantum adversaries. And also, we are in this AI reality. So AI can help the developer, researchers, but also adversaries. So who can win the game in the long run? So that's a very critical moment for cryptographers and everyone, researchers, computer scientists. And another thing is we should never forget the societal impacts for technology. Who gets the tech benefits? And how to make this smooth transition in terms of when we embrace our new technology. We should not forget about like the who can this really benefit? Do we really create a technology and then makes the world more desperate or depressed, right? So this is something we should all think about. Okay, so thank you very much. This is my presentation.
Thank you very much, Feng Hao. As you have heard, we had a loud clap for you. It was a very interesting talk. I'm going to invite a few questions before we get to our next session. Does anybody have questions for Feng Hao? Oh, it worked. Great.
You mentioned that hash-based was one of the options for post-quantum cryptography. Are hashing algorithms not affected like RSA or encryption algorithms are by quantum computing?
Yes, so currently, the kind of the only things that are affected are, say, RSA and discrete log. They can be explicitly solved by quantum computers. But the symmetric key cryptography, like hash, like SHA, like AES, the impacts are relatively smaller. So currently, the perception is, hey, if we just double the key length of AES or the SHA, then quantum computers, we don't know like how to whether quantum computers can have any non-trivial advantages over that. So that's the current perceptions, but um, who knows, right? So it's yeah, I cannot guarantee because maybe some more novel research can come up tomorrow. But if I really want to bet, I would say this is kind of unlikely.
Thank you.
How come we're making stuff that's like more complex to like head on face the quantum computer instead of just encrypting it in a way that like the quantum computer couldn't even read, like a different language instead of math?
Um, so it so for computer science, it's say if you want to express everything, say everything is kind of math. So if you want to write a language, then that is math. And yeah, we kind of need to like encode. Say if you want a computer to read or write on anything, you need to encode it using some sort of symbols. And then in this sense, yes, this you need to think of that as some mathematical equation or as mathematical symbols. So can you define a language without secret key, and this is not intelligible, and with secret key that is you can understand it and say, and then basically this is the goal of encryption. But the question is, can you really prove without secret key you can learn nothing? So how can you like formulate this intuition into a proof? And then this is basically what all the say post-quantum crypto or the cryptographers are trying to do.
One example I thought of was maybe like a DNA thing. I don't know, would that work?
The DNA.
Like you have to like put
Uh,
your DNA in to like access it, and then like even like a great computer, would that be able to bypass that?
so if say the um um so the first thing is kind of uh it, it say this is kind of um, if you are entering your DNA into something as a secret key, then this is how you can generate the secret key process. But the encryption process is you are trying to send, say, message from party one to party two. Say, so how do you generate the ciphertext? This is the process, and this is kind of um, a little bit more complicated or more difficult than just entering your DNA into the system. So we need to specify how you generate the ciphertext, and you cannot just say, hey, I enter my DNA and the ciphertext is generated. So we need an explicit procedure to consider. And I think what you mentioned is more like say how do you input the password or your secret key, but say after you enter your secret key or password, we still need a procedure to generate the ciphertext.
Okay, thank you.
Hi, my name's Morgan. I just had a quick question for you. How worried do like average people need to be, people who aren't necessarily within this realm of quantum computing, computer science? How worried do they need to be about their right to privacy, and how likely do you think it is that their information is at risk here? Is the cryptography keeping up with the quantum computing nowadays, or what are your thoughts on that?
So currently, yes, the cryptography is keeping up with quantum computing. So NIST post-quantum cryptography core has played an important role to accelerate the development or deployment of, say, crypto against quantum computing. So, but for say for everyone for broader audience, say is your data safe? So this is kind of a question, say more relevant to all different aspects. For example, how would you use your data? Is your habit good or bad? Do you kind of leak your secret key periodically, or do you go to like those phishing websites? So these are a little bit say orthogonal to cryptography itself or for the technology itself. So it's kind of secure security training and education. This is kind of more relevant to say broader audience. But say suppose the secure training, say if normal person has done like rigorous or basic secure training, and then the post-quantum cryptography, the technology is there, so that person should have sufficient confidence in his or her data security against in the presence of quantum adversaries.
Thank you.
All right. I want to ask one last question, Fengo, before we let you go. So the basic, and then I'm going to take you back to the foundations and some of the math problems there. If you wanted to encrypt something, you want to make it hard so that somebody else will not be able to figure out. And the celebrated result you talked about had learning with errors, where errors come to the rescue. We don't normally associate errors with good things, so they're bad, right? But in this case, it helped us to make an original problem to be cracked difficult. And so that's great. And then you did say your own research and so on. The very thing that was coming to the rescue is inefficient. And so you want to make it faster for your crypto system to work. And one of them was rounding. And so,
yes.
And I know you mentioned that and you didn't have time to go into it. But the thing that would come to an average mind is if the savior, which was the errors, is now being like replaced with something that's rounding, it kind of feels like it's going to be easier now to solve the problem, but that was not the case. The result you mentioned, your own research and so on, says it's as hard as the original one. So where is that, like at a high level, where is that coming from? Why is it not lost? Like the rounding still would be as hard as the original one. Could you comment on that?
Right. Let me comment on this. So now I'm back to this learning with error, this picture. So say the beautiful part of this learning with error is we only need to increase the error distribution by a little bit. So it follows from some Gaussian distribution, so that the LWE problem suddenly becomes very, very hard. So consider if there is no error, this is completely easy. If the error is too small, it always be 0 or 1, and then maybe this is also kind of easy. But if you slightly increase a little bit more, and then the error becomes the problem suddenly becomes very, very difficult. And so when the error is not big, and then the problem becomes hard, and then we can also build the crypto system. And intuitively, if your error is super large, and then the problem becomes information theoretically hard, information theoretically hides the secret S. But on the other hand, we cannot use it to build crypto system because the error is too large. You cannot, the crypto system cannot decrypt. So kind of this is an interesting balance between hardness of the problem and also the crypto functionality. So now, if the error is kind of small, and then you can think of like if you kind of do rounding, it's you can think of like for example, if you have 1.1, you get rid of the point, the floating point, you get 1, and if you have 1.9 and you round it to 2, something like this. So if the error is small, and then by scaling the problem appropriately, and we can kind of think of rounding as, because you add error, and it won't affect, or it just looks like the effect of rounding, even though this is not super precise. There is still a little bit mismatch. So so my work, my research is to show that, hey, even if you can make rounding and adding error like synthetically, they look alike, but they don't match. But this mismatch will not affect the the hardness. So that was kind of my my research.
Okay. All right. Thank you so much. That's very helpful. We are going to be moving to the next one. So thank you again, and see you next time.
Okay, thank you, Asifa. Thank you all. See you all.
Wonderful.